let's now start on the induction motors, what we did. I'll try to recall what we did earlier. We basically looked at the constructional features of the induction motor. We looked at the principle of operation of the induction motor, before which we said what is a revolving magnetic field, how it is created. Then after that, we actually looked at the equivalent circuit by looking at the total power that is being passed on from the stator side to the rotor side, right? And we, based on that, wrote the equivalent circuit, looking at the transformer equivalent circuit originally, and what happens when the rotor rotates or the secondary rotates, what happens to the equivalent circuit. So we drew the equivalent circuit on the whole somewhat like this. This is R1, this is X1. We also said that we are going to have the core loss and we are going to have the magnetizing reactance, which we wrote as Xm and Rc, right? Then we wrote actually that there is going to be a leakage reactance, which is actually X2 dash. Originally we wrote that as Sx2 dash. Now we have actually converted the rotor EMF also into stator frequency. That's what we did by dividing it by S. So because of which, what we got here, let us say, was E1, and this became directly E2 dash, which was also equal to E1 because of the turns ratio. That having been taken care of, E2 dash will be equal to E1. And we wrote two portions of the resistance. One we wrote as R2 dash, which is the inherent resistance of the rotor transformed into the stator side. And we wrote one more portion of the resistance which represents the mechanical power, which we showed as a variable resistance, which is R2 dash by S multiplied by 1 minus S. Right? That represented the mechanical power. And then we said this represents the short circuit that is there in the rotor of the cage induction motor or in the slip ring induction motor, which we create a short circuit external to the rotor, right? This is the equivalent circuit we drew, and then based on this we actually wrote the torque expression. If you may recall, we said that is actually 3I2 square R2 multiplied by 1 minus S by S omega S, right? Sorry, omega R. And then we actually crossed omega R, we wrote it as 1 minus S times omega S. So we could remove the 1 minus S from the numerator as well. So we wrote this as 3I2 square R2 divided by S omega S. I can write this as I2 dash square R2 dash or I2 square R2. It doesn't matter because the power is invariant, whether I look at it from the primary side or the secondary side in a transformer or from the stator side or rotor side in an induction motor. So this is going to be invariant. Then we wrote the expression for R2, I2. So we said I2 dash is equal to I1 if I neglect whatever goes as I0. So if I0 is neglected. And we chose to neglect it because we wanted a simpler expression in terms of V1 itself, whatever is the voltage that is being applied. So I am applying a voltage of V1 here. So when I write the entire expression with respect to V1 per phase, I can write I2, we wrote it as V1 divided by R1 plus R2 dash by S plus J times X1 plus X2 dash. This is what we wrote. So from which we could get the overall expression for the torque as, I am just substituting for this I2 dash square from here. So that is 3V1 square divided by R1 plus R2 dash by S the whole square plus X1 plus X2 dash the whole square. That has taken care of I2 dash. Now I am just writing R2 dash divided by S omega S. Right? So this gives me the overall torque expression, from which we talked about two different situations. One was when S is very much less than 1 or close to 0. Right? Which is the normal operating situation of an induction motor. Normally, if you look at most of the induction motors, we are going to have the rotor copper loss to be generally very, very small as compared to what is coming into the rotor. If I say 100 watts are coming into the rotor, I may have only 4 or 5% being dissipated generally as the rotor resistance loss. So I'm going to have almost 95% being converted into mechanical output, which means I am going to have actually slip to be only about 5% or even less. So that's the reason why we say slip is generally normally much less than 1, corresponds to the normal operating region of the induction motor. We are not going to have very large slip normally in an induction motor, which is fairly well designed, and generally induction motors are fairly well designed. So in which case we are going to say 3V1 square R2 dash by S divided by, I am going to say that this component is going to dominate over this as well as this. So I can afford to neglect X1 plus X2 dash as well as R1. I am just doing an approximation. Clearly when we do the actual calculations we will not, but we are going to have this as R2 dash by S the whole square. So this is approximately equal to this, because of which I am going to have TE is going to be proportional to slip, because R2 dash by S whole square at the bottom and R2 dash by S on the top, I will get basically S coming at the top. So I am going to have TE is being proportional to slip whenever the slip is going to be really, really small. On the other hand, when we say when the slip is close to 1, which is equivalent to the starting condition. Starting condition omega r is 0. If omega r is 0, the slip is 1. So when I am going to have the slip equal to 1, I am going to have rather this portion, that is this entire portion is going to be negligible as compared to X1 plus X2 dash. So I can directly say that the torque is going to be proportional to 1 by S. This is what is going to happen during the slip close to 1, or slip is very close to the starting condition. So on the whole, I should be able to draw the characteristic somewhat like this. Let's say this is omega r increasing and this is torque in the increasing direction. When omega r is equal to synchronous speed, so if I take the point where it is omega s, when omega r is equal to omega s, at that point, if at all ever the rotor reaches the synchronous speed, which can never happen in steady state, if at all it happens, then I am going to have really no rotor current at all, no torque at all. So it is essentially no load condition. If I am talking about rotor having reached synchronous speed by chance, by hook or crook, I am going to see that there is no rotor current, there is no rotor EMF induced, because of which there is no torque. So if there is no torque, it is as good as no load condition. That means that is torque equal to 0. So this is going to be the operating point when I am talking about synchronous speed being the operating speed. And as I increase, the load on the motor, maybe I ask for more and more load, more and more mechanical torque, definitely I will require more and more rotor current. Only if there is more rotor current, there will be more torque developed. Only if there is more torque developed, I am going to sustain the rotation of the induction motor by meeting the torque demand. Otherwise, there is no way the sustenance of the rotation will not take place. So, I am going to have, as I increase the load further and further, I am going to have reduction in the speed. Reduction in the speed means increase in the slip, because omega s minus omega r. That is what contributes to slip. So if there is a reduction in the speed, so here omega r decreases, or I should say slip increases. That's what happens when I am looking at, the speed coming down and the torque increasing correspondingly. So this is very clearly whatever we wrote earlier, that is TE is proportional to slip. So that is valid in this region. If I say from A to B, this is AB. Region AB corresponds to torque is proportional to slip. Whereas, if I am going to talk about the other region, which is TE is proportional to 1 by S, that is actually corresponding to this region where this is actually S equal to 1 and this point is S equal to 0. Right? That is where the slip is 0. So, obviously, I will have, some kind of hyperbolic characteristics, maybe something which will be somewhat like this. So, I have two portions of the slip torque characteristics clearly, one corresponding to the slip being proportional to the torque, the other being proportional to 1 by S, the torque being proportional to 1 by S. Now, S is 0, TE is 0. Yes, this is TE. Right? S is 0, TE is 0. S is 0, synchronous speed, there is no rotor induced EMF, there is no rotor induced current, so obviously TE will be 0. Right? So, we are looking at now wherever it intersects. So, I can draw the entire slip torque characteristics on the whole or speed torque characteristics on the whole as though this is the way it works. Actual speed torque characteristics will be somewhat like this as far as the induction motor is concerned. This is definitely not a linear region, whereas this is the linear region, and this is going to be slip equal to 1, this is slip equal to 0, this is going to be omega r equal to omega s, this is omega r equal to 0. Omega is increasing in this direction. Right? And this is TE. So this is the typical speed torque characteristics of a three-phase induction motor. Right? I asked you guys to derive where TE max occurs. At what slip? So we had an expression for TE. Let me write it all over again. 3V1 square divided by R1 plus R2 dash by S the whole square plus X1 plus X2 dash the whole square, R2 dash divided by S omega S. This is what we wrote as the torque expression. Yeah. We are neglecting it just to get the ease of the entire derivation. The proof of the pudding is in eating it. So ultimately, if your actual characteristics almost resemble this, it's all right. and it does resemble. So that's the only reason we are going along with it. Otherwise, we would definitely say that's the reason when I talk about the open circuit test or no load test and short circuit test, in the transformer and induction motor, there will be slight differences. We will look at it also. There will be some differences. Right. So, when we are looking at it this way, now we have to write dTe divided by ds equal to 0. I am going to leave this to you guys to differentiate. I hope you guys have done it already probably. If you have not done it, you can find out. So, this is at what slip? You can find out, and that will come out to be S max T. I am writing this as the torque is maximum, slip at maximum torque. That's what I mean by S max T. This is a slip at maximum torque. It will come out to be R2 dash divided by R1 square plus X1 plus X2 dash the whole square root. Right? In fact, you will get S square equal to R2 square divided by blah blah blah, because of which I should be able to write this as plus or minus actually. Please note, the slip is positive at some torque T max. The slip can be negative also at some other torque T max, but the T max will be in all probability minus T max, which means there will be a mirror image kind of characteristics on either side. One thing I want you to realize is, slip is positive means omega r is less than omega s. If slip is negative, that means omega r is greater than omega s. Very clearly, right? Because omega s minus omega r, that's what we said as the slip speed. That divided by omega s gives me the overall slip. That's what we said. So, and we also said very clearly that this can never happen in an induction motor. We said that omega r can never even reach omega s, leave alone going beyond omega s. For this to happen, I will have to have a condition where the motor will be driven, the machine will be driven by an external prime mover. If let us say I have a vehicle which is fitted with induction motor, right, and it is moving downhill, then definitely the gravity will make the speed go up unless I control it. So the gravity can make the speed go up beyond whatever is the synchronous speed also, for what you know. In which case, it can go into slip being negative. That's what I mean by having a prime mover. The prime mover can be a turbine, the prime mover can be a wind turbine or IC engine or whatever, it doesn't matter, but it can also be gravitational pull. So if the gravitational pull is actually acting like a prime mover, and if the speed goes beyond whatever is the rated speed or synchronous speed, that is going to cause the slip to go into the negative region. And if the slip is going into the negative region, and if I have a prime mover, in all probability, the mechanical energy will be converted into electrical energy. Right? I am giving mechanical energy with the help of maybe the gravitational pull, which is a kinetic energy. That can be converted into electrical energy, in which case the induction machine until now what was operating as a motor will start functioning as a generator. So this will correspond only to induction generator operation, where I am going to convert mechanical power into electrical power. Whereas this happens in motoring region, where I am going to have very clearly electrical power is converted into mechanical power. I am not going to elaborate further on the generator region because that will take its own 2 hours at least. So let me not get into generator region because we were only primarily concerned with the motoring operation, but nevertheless at least I thought I should make a passing mention at what point a machine which is definitely it is going to have functionality of both generator and motor. Definitely any electrical machine for that matter will have the functionality of a motor as well as generator as long as you make the situations conducive for one particular operation or the other particular type of operation. We are primarily concerned with the motoring operation, but incidentally when we encountered a negative slip, that is the reason why I just mentioned this. No more of generator. I will not talk about generator anymore. So, now this point which probably corresponds to the maximum torque, right? That we will again calculate by substituting this slip value into this. Okay? If I substitute this maximum slip value into the torque expression, I will get what is the maximum torque. This is T max. We incidentally call that also as breakdown torque. TBD. TBD is the maximum torque an induction motor is capable of generating under a particular voltage, under a particular frequency condition. That is breakdown torque. If you try to load the induction motor beyond this particular torque, it will stop. It will stall. It will not be able to run anymore. So let us say I was working with maybe 10 Newton meter, 20 Newton meter. I kept on increasing. Maybe it came up to 50 Newton meter. Maybe 50 Newton meter happens to be my breakdown torque. If I try to go to 51 Newton meter, the machine will come to a standstill situation. It will not be able to work anymore. It will not be able to rotate anymore. So breakdown torque is the maximum torque that can be delivered by the induction motor at a given voltage, at a given frequency, because I am generally operating it from the grid. The grid voltage is fixed normally, right? It will be about 400 volts, 3-phase line to line, and 50 hertz roughly. So for that voltage and that frequency, it is kind of set in stone for a given induction motor because it depends heavily upon the parameters of the induction motor. And this is S max T. Slip is increasing in this direction. I hope you understand. Slip is starting from 0 and going towards 1 in the opposite direction to that of the speed. Right? So the slip is increasing in this particular direction. Yeah. Yeah. See, if I am talking about actually a load torque like this, there is only one point clearly and it will normally settle closer to synchronous speed. I hope you got the question. If I look at any of the load torque here, if I look at some load torque like this, I will have 1 point here, 1 point here. So if I am having 2 points like this, then what is going to happen? Where is it going to settle? That is the question. Okay? If I have a constant torque load, for example, let us say I am talking about an elevator. Elevator is driven by an induction motor, let us say. So 8 of us have gotten. Maybe the torque corresponds to some value like this. Right? It is starting from 0 speed, clearly. So unless I have some amount of torque in excess, there is no way acceleration will take place. I hope you understand. I will have acceleration possible only if my starting torque, which is TE starting, is greater than TL. TL I am talking about as a particular value of load torque, which is a constant torque load. So unless I have some amount of excess available, the machine is not going to accelerate. So the machine will start accelerating. As it accelerates, please note that I am going to get more and more electromagnetic torque. Are you getting my point? This is the ordinate which represents the electromagnetic torque. So the electromagnetic torque available is more and more and more. So the machine will accelerate further and further and further. So this is the starting condition. It is accelerating. And the moment it accelerates and reaches this value, it will accelerate further. And when it accelerates further, and the torque is decreasing. So when it is not really feeding into its own self, that is where stability is. Otherwise, there will not be stability. So the stability happens only in the linear region, not in the hyperbolic region. So wherever the stability is, it will come and settle there. So it will settle down at this point, which is probably P1. That is going to be the operating point. On the other hand, instead of 8 people, say 18 people have gotten into the elevator. The torque is very large, the demand. If the torque demand happens to be somewhere here, the machine will not start at all. It will just stall. It will say overload and wait. The elevator definitely will have an indicative button that it is overload. Because the load torque is greater than whatever the machine is capable of generating at the starting condition. So that's a very good question, very valid question. So the starting torque has to be greater than the load torque for the machine to start. Otherwise, it's not even going to start. Right? Are you getting my point? The starting torque has to be greater than the load torque. Unless it is greater than the load torque, I am not going to be able to see the machine starting. So generally, the operating point, what we specify, will be less than the starting torque, invariably. That's how it will be. So you will have only one of the operating points possible, which is actually coming over in the stable region rather than in the unstable region, where it is just going and going, increasing in terms of its speed. That is essentially unstable operating point. So the stable operating point will be only this. So P1 will be the operating point. Now, let us try to write the expression for TE max. I want you guys to verify the derivation. Please do it, because I remember this by heart, surprisingly. Generally, I don't remember many of the expressions, but I remember this. So this is going to be R1 plus R1 square plus X1 plus X2 dash the whole square root. This is what I remember. This will be again plus or minus. I am only showing plus. Minus will correspond to generator region. I am not really going into generator region. Okay. So this will be the TE max. One thing I would like to point out here in TE max does not depend upon the rotor resistance at all. It doesn't depend upon the rotor resistance. Although all along when we were talking about the torque, we always said I2 square R2 by S omega S. So R2 was playing a very, very vital role. But TE max does not depend upon R2. It rather depends upon R1 and X1 plus X2 and so on and so forth. Right? But the slip at which the maximum torque occurs, that has R2 in the numerator. Which means as I increase R2, if I increase R2, like in the case of a slip ring induction motor, where I can include resistances from externally. Okay, so if I am going to have R2 increased, then what is going to happen is, this maximum torque will not get affected, but the S max T will get affected. S max T will shift towards 1. So what is going to happen is, I will have probably one more characteristic somewhat like this. One more characteristic somewhat like this. So I'm just showing how exactly the characteristic shift. Please remember, this is what is S max T now. So this is S max T1 when I increase the resistance further. And this is S max T2 when I again increase the resistance further. Rotor resistance, not the stator resistance. So I should very clearly indicate this is R2 increasing or R2 dash increasing. Either way is fine. If I am able to increase R2, maybe like in a slip ring induction motor, which I cannot do in a squirrel cage induction motor. I just cannot do that in squirrel cage induction motor. I can modify the resistance characteristics of the rotor by including an external resistance only in the case of a slip ring induction motor. So if I am talking about a constant torque load, I have one operating point here, one operating point here, one more operating point here, which means by changing the resistance, rotor resistance, I will be able to get 3 different operating speeds when I include more and more resistances. So the rotor resistance control for controlling the speed of an induction motor at a given torque is possible only in the case of a slip ring induction motor, which is a big plus point because I am incurring losses, all right, but I am able to get a very simple method of speed control. If I want to have speed control, no matter what, I don't mind losing out on efficiency. In that case, one of the best means possible is to include rotor resistance. Because it's very simple. Just include rheostat, keep changing it. That's it. It's not a big deal. So, if we can do that, that really gives me the leverage to have variable speed at a given torque that is possible only in slip ring induction motor, not in squirrel cage. So, this is one of the major plus points of the slip ring induction motor. Although it has no maintenance free operation, it is costlier, it has wear and tear, all those things are there. Nevertheless, this is one of the simplest means of controlling speed of the induction motor. Right? So, now that we have seen the slip torque characteristics or the speed torque characteristics, and we have also got what is the TE max expression. Please note, for all these resistances, still TE max is remaining the same. That has not changed. TBD has not changed. Right? I would like to emphasize that. We have not changed TBD. Only thing that has changed is the slip at which the maximum torque occurs and the speed also can be varied. So much so for the slip torque characteristics or the speed torque characteristics of induction motor. We talked so much about R1, R2 dash, X1, X2 dash, but we didn't talk so far as to how to determine them. So let us try to go and see how to determine the equivalent circuit parameters of the induction motor. How are we going to determine the equivalent circuit parameters of a 3-phase induction motor? We all are already familiar with transformer, how to determine the equivalent circuit parameters. We had seen open circuit test and short circuit test. As induction motor is very similar to a transformer, similar tests are going to be able to determine the parameters for this machine as well, no doubt. But how will I open circuit the induction motor? If I open circuit the induction motor, it's not going to rotate. and the secondary side is anyway short circuited in a cage motor. I can't get in and then break the end ring connection and say it is open circuited. I don't want to do that. So how am I going to really do the open circuit test? Rather than doing open circuit test, what we do is no load test of the induction motor. We are just going to allow the motor to run freely. Free running test. We call it as free running. It is running freely without being loaded. I'm not going to load it at all. So you are going to have essentially no load test being done when the motor is running freely without being connected to any other or coupled to any other mechanical load. Right? When I am going to have no load test, you think about the induction motor characteristics. I am going to have rather equivalent circuit. This is R2 dash by S. This is X2 dash. And this is V1. This is R1. This is X1. Of course, I do have RC and XM. When it is running freely, it is as good as no load. The torque is 0. When the torque is 0, the slip will also be close to 0, if not exactly 0. Slip will be close to 0 because I am asking for literally 0 torque. I don't want any torque. That means the rotor current will be almost close to 0. The rotor current will not literally flow. It may have very, very minuscule value. So the no load condition is as good as having the rotor circuit impedance to be infinity or the rotor circuit being open circuit completely. It is equivalent to that. I will not say it is that. It is equivalent to that. Slip is almost close to 0 under no load condition. If slip is almost close to 0 under no load condition, R2 by S happens to be infinity. If R2 by S is infinity, it is as good as open circuiting the rotor. So no load condition almost mimics the situation of open circuit condition of a transformer in the case of an induction motor. So that is the reason why we conduct normally no load test, or we also call it as free running test. So under free running test condition, we normally apply no load on the shaft and try to measure what is the power. So what we are going to have is, the circuit diagram is somewhat like this. I am going to have 3-phase supply. I will have a 3-phase variac or an auto transformer. So I am connecting the full supply to the variac, and I am going to have 3 jockey points coming out like this, which will go to the 3-phase induction motor. Right? I can't do it per phase, obviously. I have to do it for 3 phases and then calculate per phase parameters. Now here is my induction motor. So induction motor, let me show it like this. This is my stator. The rotor I can show internally, but I have written big IM, so I don't want to show it there. Otherwise, this is the way I will show the squirrel cage rotor. If it is slip ring rotor, I will show it like this, as though 3 windings come out. That's it. So this is slip ring or wound rotor, whereas this is squirrel cage rotor. Okay, so representation, I am just showing the representation. So this squirrel cage rotor, now please note I will not show any brushes. In DC machine I will always show brushes in the armature. Here I should not show a brush. Now this will be connected through wattmeter and ammeter. And voltmeter, of course, we can connect, or multimeter can do the job of measuring. So I am going to show 1 wattmeter, 1 more wattmeter, and I am going to show the pressure coil. 2 wattmeter method we are using, right? So I am going to have one more pressure coil here. Potential coil and current coil, right? Recall this? We were talking about this when we were initially talking about 3-phase circuits also. So this is M, L, mains, load, and this is going to be the common point, and this is the voltage point. This is common, this is voltage. So maybe M1, L1, M2, L2. This is V2, this is V1. Right? Now I will connect this directly to the induction motor. So I am going to show as though this is connected here, this is connected here, this is connected here. I can connect a voltmeter if I want here. Of course, I should have connected an ammeter which I missed. Of course, ammeter should come, definitely. Assuming that the 3-phase induction motor to be balanced, it will be balanced normally. So 1-phase current if I measure, it is good enough. It can be star connected, it can be delta connected, it doesn't matter. I'm going to get one W1 and W2. 2 wattmeter readings. So W1 plus W2 is going to be W0. This is of course 3-phase, 50 Hertz, 400 volts, AC. What is available in the lab normally. Right? So you will apply rated voltage to the induction motor by using a variac, slowly increase the voltage. So you will not see a jerk of current suddenly flowing into the motor. So you will slowly increase the voltage and the motor will start rotating. You will bring it up to the rated voltage. You will measure what is the value of ammeter reading, and you will also get the voltmeter reading, and you will also get the wattmeter readings. Under no load condition, the major current drawn is by the magnetizing reactance core loss component of resistance. Generally, core losses should be as minimum as possible in an induction motor, because I would have laminated the core. Hopefully the hysteresis losses will also be not too high, but there is one loss which we cannot account for, that is rotational losses. Definitely there will be some amount of rotational loss. There will be friction whether I like it or not. There will be some amount of windage whether I like it or not. So there is going to be some amount of mechanical losses which I cannot account for. Most of the times in induction motor equivalent circuit, RC would also take care of these mechanical losses. Very often we might club everything together and say, let RC represent it. Because it's very difficult to bifurcate or, partition all the losses independently. Very often it will become very difficult for us to partition the losses. So we might take the complete mechanical losses during no load test plus whatever is the core losses, everything put together, we might call that as RC, right? So the current drawn is primarily due to the magnetizing current if I say RC is not having much of losses. If magnetizing current is the primary current that is being drawn during no load condition, the power factor is going to be bad, really bad, because magnetizing current is always inductive in nature. If it is inductive, I'm going to have 90-degree lagging current. And if it is 90-degree lagging current and RC current is a small current, then overall current is going to be extremely lagging. If it is extremely lagging, I will have in 2 wattmeter method, if you may recall, cos of 30 plus phi in one of the cases, cos of 30 minus phi as the other case. The wattmeter readings correspond to VL, IL, cos 30 plus phi, VL, IL, cos 30 minus phi. If phi is greater than 60 degrees, lagging, then in all probability, one of the 2 wattmeters definitely will kick back. You would see that the needle goes below 0. So you will not be able to read the wattmeter at all. 3-phase wattmeter will automatically add and give you the overall power. So generally I insist on using 2 wattmeters so that you guys are able to see this kicking back phenomena. It is important to see that. Only then you are going to realize that when the power factor is really bad, I am going to get very clearly a kicking back in one of the wattmeters. If one of the wattmeters kick back, then what we will do is to reverse the current coil. That means you have to disconnect and reconnect the current coil. That's what we will do normally. So M will go towards the load side, L will come towards the supply side. If I just reverse, 180 degree out of phase will automatically make one of the 5, whatever we have 30 plus 5 or 30 minus 5, come out to be maybe 180 minus or something like that, because of which you will automatically see that the reading becomes positive. So you would not have this difficulty if we are talking about reversing the current coil. But whatever you got as maybe after reversing, you will get a positive reading, but note it down as minus so and so watts. So let us say W1 was 100 watts, W2 was minus 50 watts originally. So it was actually showing kicking back, but after reversing, it has shown 50 watts. So you will show W1 as plus 100 watts, W2 as minus 50 watts. Is that clear? So this kicking back would normally happen in most of the induction motors, if it so happens that it is a well-designed induction motor with very minimal requirement of magnetizing current. Right? So this is the no load test. So I am going to have W1 plus W2 equal to W no load. And I am going to have V no load and I no load. These are the readings that I get. R1 I would be able to measure just with the multimeter. It's not a big deal. R1 is the resistance of the stator winding. I can always connect maybe between 2 terminals of the induction motor stator. I can connect a multimeter. If it is a star connected, it will come out to be R1 plus R1. I hope you understand, because 2 of them will come in series. If my stator winding is in star and I put a multimeter between these 2, it will come out to be R1 plus R1. So whatever I get as the multimeter resistance, I have to divide that by 2 if it is a star connected induction motor. If it is delta connected induction motor, I will have R1 in parallel with 2R1, right? That's how it will be. I hope you understand. I am going to have R1 in parallel with 2R1. So it is going to be 2 by 3 R1. What I get will be, I think 2 by 3 R1, because of which I should be able to calculate again backwards what is the value of R1 from here. So I can simply use a multimeter and measure the resistance. That is not a big deal. I have measured the resistance. I have done the no load test. Now, in the transformer, we conveniently neglected whatever was dissipated in this R1, because the current was less than 5% under open circuit condition of the secondary. We could neglect it completely. Whereas here, I can't afford to neglect it completely because of the fact that the current drawn under no load condition happens to be anywhere between 25 to 30-35%. This is true in the case of a large induction motor, about 20% or something. If it is a small induction motor, again what we have in the laboratory and all, we couldn't care less. So if you look at actually the value of the no load current, it can be as high as 50% even in many cases. So it's very large. Normally the no load current is very large, because of which we will say W no load minus 3I no load square R1. This will be the actual mechanical loss plus the core loss. This will be the actual mechanical loss plus core loss, which will help us to calculate RC. Okay? Please remember all the readings are for 3-phase. So if it is a delta connected motor, V no load will be equal to V0 per phase, V0 per phase. But if it is a star connected motor, V no load divided by √3. I have to do the conversion, everything on a per phase basis. Similarly, what I have calculated now as the actual core loss plus the mechanical loss, I have to divide that by 3 per phase. Ultimately, whenever I do the per phase calculation, I better not forget converting everything on a per phase basis. I have to do that. Unless I do that, I am bound to make mistakes. Okay? So we will continue with the no load test and the second test, which is equivalent to short circuit test.